Good afternoon. I welcome you all. I welcome you all to the technical session. Sir, on करो उसके बंद. Off कर लो. I am profoundly delighted to take an opportunity to invite Dr. Ranjan Kumar Behera, sir, to this technical session. Ranjan Kumar Behera received BE degree in electrical engineering from the Regional Engineering College, now it's NIT, Rourkela, India. The MTech and PhD degree from Indian Institute of Technology, Kanpur, India in 1998 and 2003 and 2009 respectively. He worked at Hindustan Aeronautic Limited, Sunabeda, as trainee engineer since May 2009. He is a faculty member in the Department of Electrical Engineering at IIT Patna, where he became head of the department in January 2016 to 31st March 2019. During July 2008 to February 2009, he was as a visiting scholar in the Energy System Research Center, Tennis Technological University, USA, and also as a visiting research collaborator at ECE Department, University of Pretoria, South Africa, during July 2016. He got several national and international awards, such as Young Scientist Award in Engineering Sciences from DST, Government of India, 2001, selected as the featured engineer of the Globe 2015 USA, and Vaskar Advanced Solar Energy Award, Indo-US Science and Technology Forum 2014 for doing solar research in Energy System Research Center, USA. He published 134 research articles in different national and international journals and conference proceedings. His current research interests include power electronics, high power motor drives, smart grid, and IoT applications. He is co-authored a book entitled Power Electronics, Drives, and Advanced Application by CRC Press, April 17, 2020. So we are very much fortunate that sir is with us, and he will share his some of the knowledge with the participants. So I duly welcome you to this program. So please, over to you, sir.
Thank you. Thank you very much. And I must thank to DRIEMS institution, especially to Dr. Pradhan and Dr. Sushant Sethi for inviting. So I'll try to discuss some of the concept which we are in the designing. We are now doing this completely. We are designing that one. And I don't think that is. So is it coming?
Yes, sir.
Full screen is coming on. Okay, just 1 minute. I'll share the PDF. Maybe that's yes. Okay, good morning to everyone. So today, whatever we did some research or whatever I have learned, we have a project called the Smart Grid Planning and software design of a smart microgrid. Planning and software design of a smart microgrid by imprint. So this project mainly three different institutes. We try to solve this, and one is IIT Guwahati. They are making the software planning tool, and IIT Kharagpur also designing the software planning tool for the microgrid. And my part is I am designing the switch network for designing the as a hardware component of the, according to planning and design, is a modular power electronics converters connected to the microgrid system, and complete switch network system is designed. Okay. So this is a big research. We are only doing some portion of this one. If the planning and design are always different for different kind of geological environment or geological structures in our earth. So if you see somewhere that, for example, in Bihar, so wind generation is very low. But in the other part of India, wind is very good. Like especially those are coastal areas, the wind is very good. So planning is a very important thing. And without planning and design, for example, we put a one microgrid of 1 megawatt solar system in the Port Blair Air Force Station. So designing there is completely different as compared to our land here, because completely sand particles they blow in the wind, and wind contains also small particles of sand, so which may struck to your solar panel, and it may become low efficiency also. That is what different designs are different, and that's why planning is the most important thing before design. So already Madam told my life's journey, and where we have spent some time. We do research on many activities like solar, wind, power electronics, high power drives, especially in the megawatt range. Also, we develop the drives, and especially shipboard power supplies, and especially the traction motors, the Indian Railway drives, which is more than 6,000 HP, nearly 4.5 megawatt drives. So we work on very high power. We don't work on the very low power drives. And also some of the drives on the BLDC drive, SRM drive, and different induction motor drives, multi-phase also we do, and wireless power transfer, smart grid, and electric vehicle design. Okay. So this is our new book by CRC Press. So what is the electrical power challenge today? First thing is aging infrastructure. So long back, the conductors, everything was connected to our grid. And the grid became a very old structure, which lot of maintenance is required. Second one is reliability, also another challenge. And then security, then market dynamic, which in India, we don't need to worry for this one, because in India, we have only the connected to the grid, which is supplied by the government. And rate and pricing and distributed generation. That is one of the important factors in India, that somewhere you have a grid connected system, somewhere you don't have a grid connected system, and seamlessly transferring from the islanding condition to the grid connected system and grid connected system to island system. It till today is a big challenge. And second one, when you have a distributed generation, if there is a grid fault, That is also another challenge because there is a limitation in the current from the distributed generation. So many things are really today challenging because when you practically implement this, you can understand these problems. But a simulated system, very difficult to understand the real picture of the grid. And efficiency and optimization techniques are very, very important today. And many in our IIT Patna also, many professors also they are working on optimization technique for optimal allocation of the distributed generation, optimal allocation of the electric vehicle charging infrastructure. Many things are there. So rising energy costs and the conservation, mass electrification, which is required today. Everyone wants electricity. And this is actually in India, there are a lot of innovation. So I visited last year to NIT Agartala, and Professor Jain, he took me to one village around 120 kilometers away from Agartala. So in that village, one lady, she whole village she electrified. And how she electrified is very, very, really we need to think that one. So she put a hook in a 11 kV line, charged to a banana plant. And from the lower of the banana plant, she got a 230 volt supply to entire village. So this is what, in the systematic way, we know that there must be step-down transformer, and you have to distribute. But you can see that even a tribal lady is so much intelligent that she could be able to do this one. And renewable energy today is also another aspect. And green energy, that means to minimize the industry's carbon footprint. So when we see a microgrid or a smart microgrid, because microgrid filling, when you do, many people, they do research on the microgrid, especially in India. Today, the researchers are driven by the microgrid only nowadays. And they do so many activities, but unless you do not put the microgrid in the practical system, everything is only a superfluous study. So when we have a different wind, solar, biomass, and so connected to the intelligent network with the sensors, meter, and then you have a load and energy flow, and you need to collect the data. So based on those data, you can control the load or source management or the load management. Or sometimes we call the demand side management, sometimes we call the source management. So there are different names altogether. The most important thing is how you want to distribute. For example, in your house, you bring four bananas, but the people are there, around 6 people. So you need to divide, that everybody should get some banana. So you will cut it and you make it that permutation combination, that how it can be distributed. And exactly like that, you will distribute in your home. So exactly similarly, when we have a load, when we have a source, you know what is the source? Is your 4 kela is the sources, but you have a load, accordingly you can distribute. These loads, some loads are required heating capability, or some require DC, some require AC, some require hybrid, both AC, DC, some require variable frequency, some require fixed frequency. So these are the work of the controller, which can control and give according to the requirement. So why the microgrid planning is required? You see here, there are different pictures I have given. First picture is a lot of cloudy, and there are a lot of snowfall. And it is hardly you get any sun. So you cannot design for a sun and solar-based system. It is not possible. And if you go to some other very barren land, and it is cloudy, and it is also very difficult to use. And there are nowadays coming floating solar system, but till today the structural stability is not there in the offshore solar plant. But offshore wind turbines are there. Today, Poland is very, very populated with the wind turbine, where they nearly 20% of their complete electricity they produce from the wind. And also, you see that in our India also, you see here in the Tamil Nadu and go to Gujarat, there are a lot of wind turbines which can be connected simply near the local end, or it is also need to be connected. So why if you see here, generally in the foreign countries, they don't like to put their wind turbine near their house because of the conducted noise and the mechanical vibration. That noise creates a humming sound in the ear. They don't get proper sleep. And there are different kind of frequency also generated. Third thing, they get very little sun power. But when the sun power is there and this wind turbine caught the sun, they feel more irritation. That's why always we try to put this wind turbine far away from the locality. Okay. And then if I have given one picture here, good side, bad side, obstacles. So what is the wind turbine? Where you need to put? You cannot put everywhere. So if there is an obstacle, that will create a turbulent wind. Turbulent wind means it will destabilize your centrifugal force of the wind turbine. So I remember I installed around 750 kilowatt wind turbine by G in Hong Kong. So in there, when we put that wind turbine, and after that, as soon as we installed that one, when we came down, the wind turbine burnt. So we thought that what is the problem? The problem was that it was not a proper site, and the site must have more, the height of the tower must be very high, so that there should be some laminar wind flow. So because of the turbulent wind flow, because in the wind turbine, how much power we can generate if we go to the basic of the wind turbine, there was a great scientist. His name was Hughes constant. Okay, name was Hughes. So what he did that that from the wind, if wind contains the 100% power, you can extract 56% of the power from the wind. So that is called the Hughes constant, 0.56% of the total power. Anyway, so these, the Behera limit, sorry, Hughes not, it is the Behera limit, B-E-T, Jack, is a German scientist, a physicist. He has developed this theorem. When you go to basic of the wind turbine, I'm not going those basics. Okay, so we will see more research-oriented things, not those things. So anyway, when you put this one, so if the wind blow, then what happened to this big turbine structure, they move. So you know that when they move that structure, the centrifugal force must be balanced all the time. And when one fin is having turbulent wind, other two fin is having laminar wind, that turbulent wind one, that will destabilize the complete mechanical structure of the wind. And such a huge structure, and that will start vibrating actually. So that is why that stability is very important, and to find out the proper site and proper design and planning is needed for that. So the wind force is turbulent, always you must increase your height of the tower. That is the most important thing. When you increase the height of tower, again, because of the loading and as well as the vibration to the wind, destabilization is very easy. That's why that is also there must be some limitation. And then when you have a different kind of structure, for example, in the hilly area with no wind power, so what you design? You need to design a solar-based system. And wherever you have both wind and solar, you can have a hybrid system. So like that, there are different combinations of design are required. That's why before seeing the geographical topology of an area, then you need to go there and need to plan. For example, we install around 15 solar power in Bihar, and we have seen that in different villages, the requirements are different. So somewhere you require directly sun feeding to, or the sun power feeding to the locality, somewhere you require the variable diesel generator, somewhere you require different kind of topology. So that is what each site will have different kind of things. So you see that the smart grid, what it comes into picture today, is the central generation, then transmission. Then we have cluster of microgrids, which is interconnected to the substation. Through the substation, it is connected to the distributed network. So how much you can do the microgrids? There are n number of microgrids you can connect. And these distributed microgrids can feed the power during the peak load. For example, peak load you require. And you need not to go to central generation system because it will burden to the transmission system altogether. So what do? We take from the local microgrid and try to solve the problem of, and that one of our professors from computer science, they are designing this distributed microgrid. They do mainly optimization technique for the load management, okay, demand side management. They do that. So these microgrids are connected until today. Also, this microgrid, like one proposal we put long back, that in a village, how self-balancing power system for a rural electrification. So what is the self-balancing power system? Because each house we put 1.5 kilowatt plant, two houses are 1.5 kilowatt solar plant, and this 1.5, 1.5, 1.5 like that. In the whole village, there are 10 sets, around 15 kilowatt power generation from the solar. Now, you see, one house is having more load. For example, one house is having 2 kilowatt load where the generation is 1.5 kilo. This is the ideal condition. I don't say that practical condition. Practical condition, if 1.5 kilowatt, only the 40% of that is the average power you will get in your house. So exactly, I am not going in the practical thing. I'm an ideal condition, I'm saying. So 1.5 kilowatt in each house, and if some house is having festival, they require 5 kilowatt of the load. So what it will be? It will not go to the grid to ask the power. It will self-management by using IoT-based device. We developed that program that if my house is having only 200 watt or 100 watt utilization, the rest of the power I can transfer to my local. And that is called the cluster of microgrids, sharing the power each other. And what condition? And so many optimizations are required, many things are required. But those things still today, people have not done this one. And there are few papers you will find that cluster of microgrids, they're balancing their own power and supplying to a demanded load. that is there. But multi-load system, multi-source system, and management of the sensor coordination with these loads, there are a lot of study need to be designed and done in the research area front. And that is still today, very few paper you will find in this regard. So anyone can do in this research. There are a lot of things. Then, what is the smart grid? You have a conventional grid, we know. In the conventional grid, you take the smart device and put it there. For example, there is a car. Put the smartness into the car, that became a smart car, or the autonomous car. So the smart system design, the smart grid cannot replace the existing grid. Because even if you want to do the existing grid to make a smart grid, it is very difficult. Why? Because the corridor or the power corridor which you have designed for certain power and certain limitation, certain equipment which is used, they are all and unidirectional equipment, where in the smart grid you require many things. So that is why there must be coexistence. And what are the component of that one? Protection, switching, dispatch, and control management. Second one is the regulatory and standardization of the components. Is the biggest challenge today. For example, we have purchased some smart switching meters, and also smart switching meters we have got from Germany. They both are not standardized because when you use in a higher frequency range, these devices are not at all responding. So that is why there are a lot of standardization and that required. And second thing is our communication, messaging, and data are today's wealth is the data. And you have data, you have wealth. So like that, if you require how we approach a microgrid research. First thing is the network approach is a very easier method. Like you have given a network system or network way of understanding a system, so you can easily solve. You can put the Thevenin's theorem, Norton's theorem, superposition theorem, and find the system dynamics. So this similar kind of the control of renewable sources with the storage and management of energy in the ancillary services and sensing and network approach allow researchers from diverse fields to work together. This is the designing criteria process. What is the design process? Like one of the student in Dr. Priyanka in IIT Bhopal, she worked on the microgrid design, the planning of microgrid design. So two of her students, they did PhD, but she only do some integration of some solar and wind and then optimize all those things. But when there was some discussion, so she called me once and we were discussing, she became very astonished that the design process is so intricacies that she was just telling that we just preliminary design we do. Because most of the time we take only a paper, we try to solve that one and with few input. But there are a lot of things now a power engineer not limited to a simple optimization problem. Power engineers need to understand the control algorithm, optimization, robustness, reliability. Complete knowledge of that will bring you an overview, bring you a holistic development of the research. So that is why in the research, generally we take a paper and try to solve it. It is not a research actually. Research means how you can add many components together to your existing research. That will give you the more innovation in the research. So when I was discussing this one, that microgrid element diverse benchmark problem. For example, I have designed a simple microgrid system which is feeding to the grid a 5 kilowatt system. That is my benchmark problem. When I add a battery to it or solar to it, there are only addition to that one. When you add, you can see that complete dynamic control algorithm, everything they come into picture differently. That's why another aspect is modeling. And how you model this one, whether you will use the small scale, a small signal modeling or large signal modeling, or whether you will linearize, or you will do completely non-linear modeling by using Lyapunov's theorem and the phrase analysis, describing function, all those things you can add together and you can make that. So this control design and power and communication modeling also we need to do. And then what are the design criteria? Because you know that in daytime you get the sun, and in nighttime you have no sun. So what is the utilization factor during nighttime? What is the utilization factor in daytime? Everything you need to be calculated when you want to design a smart system. Else it will fail, okay? So then another one is what are the standards according to grid code? I will discuss that one for a wind turbine. What are the grid code and how we will take care of those grid codes? Because I did a project for the Spanish government for the Spain. So that grid code we modeled and we gave that project long back with Professor Ojo. And then what are the data requirement and specification? Then when you get all these data, now you can control whether you are voltage control mode or frequency control, what kind of protection, energy management, load management, and demand response. Then you can use some kind of case study. For example, I have an induction motor, I give a step change in the torque. I vary the speed. For example, we design an electric motor here up to 750 RPM because we thought of it is 45 kilometers per hour. So I designed a 750 RPM motor. So like that, you need to design those type of considerations are very, very important. And what are the components of design process? One is that the benchmark problems. So you see here, there are in the right-hand side, there are different solar-based systems. And everywhere, the solar system are taken with respect to the sum of the benchmark problem, that it is like remote communities and what kind of campus microgrids and military-based system. Here we put also 1 megawatt. So microgrid, then modeling. What is the generator modeling, energy source, load, and local energy? And then what is the trade-off? In the modeling, even if you will model it, there is some assumption. For example, you have a DC-DC converter. When we design a DC-DC converter, we model it, what we consider? We consider all the parameters are ideal. And these, all the components, the lossless, so many things we consider there, and it is operating under steady state condition, then you design that one. But actually in a proper dynamic condition, it is not valid at all. So you need to understand what is the trade-off and what and how you will, if you can approximate those things. Then once you know that the model, other thing, you can design the controller. Once the controller is designed, then you can have the interface with the controller, with the communication network, and then both power and ICT modeling you need to do, because I remember we had a solar plant in Toipur village in Bihar, in Vaishali district. It was supplying to 10 houses. And our technicians, they don't want to go to Toipur village because they don't feel that going to rural area and we don't want to stay there. So we put some kind of ICT modeling and with power, and we got the data from there by putting the simple IoT based system. We got everything from here at IIT Patna. So this type of modeling need to be designed, and there are also different case studies need to be developed with the generation, storage, and load, and testing and validation we do by using, we have a real-time simulator where you can do that one before developing the real one, actually. So that is what the real-time simulator always gives us this. Then what are the design objectives? So I will see more into design objective. The design objective is that it must be environmental friendly. Second one, reliable. Third one, integrated of the variable renewable sources. For example, it should be like a plug and play. You need not to worry, oh, this wind turbine is not working, how I can connect to the grid? Yes, you can connect to the grid, but you cannot disconnect at your own will. If there is any problem or anything, you cannot disconnect that one because it will completely destabilize the network. You can reconnect, but you cannot disconnect when there is some abnormal or something fault occur. So you will see there are some video I forgot long back. In G they have developed when one wind turbine fails, how it affects on the entire grid. They have shown by putting different circuit breakers, isolators, that how one grid failure and then suddenly wind turbine is switched off, how that unbalance actually transmitted throughout the grid, they have shown by video. I don't know where is that link. I find out. Sometimes I saw long back. So this type of system design is still today is a great challenging because of the integration of the variable powered wind or solar renewable energies. Then operational cost of energy also another aspect, and that is what we need to optimize by using economical dispatch. So here our Professor Parida, SK Parida is working on this cost market values because Professor Srivastav from IIT Kanpur, he used to work on that, so he also continuing that way. So efficiency is the loss, the low loss, and then flexibility, okay, energy, whatever, flexible energy system, that is very important. So microgrid benchmark problems today all over the world, they studied in this way. One is a typical campus type microgrid, and you will find in our power system, there are different kind of microgrids, nanogrids, and even mega grids. So I visited to long back to Pretoria. They put me in the mega grid project. So mega grid project developed by the European people, and they want to push the power to the South African country. And South African country people, they don't want that power because they take those mega grid power, then they may become slave again. So they are in fearful state. So they don't purchase from them. But the European people, they are pushing them. Like that, it's going on. There are many like that grids has been developed in the worldwide also. So we will see that what is a typical campus type microgrid and then the utility type microgrid and SIGRE model. They have been given very beautifully. You see, this is a typical the campus microgrid, and this you have a point of interconnection and then we have a islanding contact and other loads are connected, and the microgrid control you have a storage and the solar system. Okay. So this type of microgrid, campus microgrid, what you have some kind of utility. For example, you have the energy meters connecting to the electrical charging station. Then you have some kind of your washing machine, refrigerator, TV. All these things are connected, and all are controlled. Each device is today controlled by some kind of smart devices by which you can easily develop. So when you see a typical campus type microgrid, it is very simple in design. If you go little higher utility type microgrid, and this is actually the photograph of a utility scale microgrid as a 25 kV overhead line. And then you have a 28 MVA star delta transformer substation. And then this is a utility scale microgrid is design. This is also the utility grade microgrid that you have a diesel generator and you have a generators, then you have a power converters connecting to the wind turbine. So you can see that these are the rating, and I have taken this one, the microgrid guidelines and design. So SIGRE, they have developed this microgrid very beautiful. This SIGRE microgrid, SIGRE is the standard, you know, all of you know, those are in power system and power electronics. They are the two IEEE model, second one is the SIGRE model, or the IEEE standard, SIGRE standard. SIGRE standard followed by all European countries as well as the some portion of the all mainly UK people, they follow that one, and IEEE model followed by especially North and South American people. So, but if you see this one, you have this is a primary transmission system, and you can have both radial as well as mesh network. You see here, that is what you can make this network as both way, and this. Each feeder where the medium voltage and low voltage transformer are used, and then this is the complete network. And this is called the three-phase section of North American medium voltage network. Okay, SIGRE benchmark. And any network you want to build, you must take this one as a benchmark problem. So simulation model, I told you, these models are synchronous generator model, modeling of renewable energy sources, transmission line where you will transmit. I will show you at the end of one video how the transmission smart line can be designed. So the load model and model of communication system. And if you see a synchronous generator model, this is a typical synchronous generator model, and it is available in all the books. So I am not going in detail of this modeling, so all of you know this. So then we have a renewable energy, for example, double-fed induction generator or PMSG, permanent magnet synchronous generator we use and connected to and then we have a bidirectional battery charge connected to the utility. So then each component you need to model. First component is your wind turbine model. Then you will model the battery. Then we will model the solar if it is available, and we will model the other component of a microgrid. So first thing is the modeling control based on the permanent magnet synchronous generator based wind energy conversion system. WECS, okay, this is wind energy conversion system. So I thought that why I will take a small model and show to you, but I have taken a complete model of this one as a 3-level, very high power wind turbine connecting to the grid. Okay, you can have the isolated grid or grid connected also generators. So we have a 2 inverter. One is our 3-level neutral point clamped converter, and there are also 3.3 level NPC converter. And these converters are connected through the grid. Now, first thing, you cannot model the complete one. First, you model with the generator side converter and generators. So, if you model this one, for example, so I have not given anything basic of the basics of the drives. So, you know that in the basic of modeling of electrical drive is that DQ modeling or this reference frame theory. Okay, I'm not going to discuss that one. So you can go through the reference frame theory. So we have a permanent magnet synchronous generator, and then we have a converter. And this is controlled through these switches. So now I will model this grid side converter. You can easily model by using DQ frame reference theory. You can have the DQ, D and Q axis component. But we have a 3 level. You can see here, we have a 3 level. So you require 2 series capacitance for this one. So what we did, we put 2 series capacitance. And that series capacitor charging or the capacitor dynamic can be written as dVc, dVdc1 by dt and dV dDc by, this is the 2 capacitor voltage dynamic. Okay. Now, this is the controller which we have designed. So I am not going in step by step, but you can, these are available in all standard books as well as standard journals. IEEE transactions also available. So this is our current control, and this is our this PI controller. And this is the modeling for our permanent magnet synchronous generator. And if you go to the double fed induction generator, there you need to develop other kind of the, there you require the transformation matrix, and it is from ABC to DQ. Many things come into picture, okay? So this is because you have a permanent magnet. That is why it is very easier for modeling. Then, when we model this one, you can see that we have a complete modeling we did, and you can see this is the grid voltage and current. In this grid voltage and current, they both are in phase with, okay? What is the in phase operation? Like we teach the students, what is the maximum power transfer theorem? When the load matches with the source, then it is maximum power transfer, or the load impedance as the complex conjugate of the source impedance, then that is called the maximum power, or the load resistance equal to the load, the source resistance is equal to load resistance, it is the maximum power. So what do you mean by maximum power? That means you have power is equal to V into I into cos phi. If cos phi is equal to 1, then V into I is maximized. So that is what called the maximum power transfer theorem, where the reactive power is drawn by from the grid is equal to 0. You see here in this simulation, although your voltage is constant, the current is varying, but always it remains in phase with the grid. Grid voltage and phase current, they both are in same phase. That is why they always maintain the unity power factor. Okay? So that is why this converter doesn't require any reactive power support. Reactive power means that power which oscillates between the source and node. Another name of the reactive power is a carrier. For example, you got a baby, small newborn baby. So how the nurse will bring to you? Nurse will bring with a lot of cotton and put around, and warmer also they will put and bring to you. Sir, this is your child. So if you see that one, the child is important, but for caring the child, you require a lot of cotton, many things are the nurse is bringing to you. Exactly. The real power is important, but the reactive power is only a carrier power. So it must sustain the age, minimal age required. Then this is our line-to-line voltage and the current. You can see this. I am not going to discuss this one. The 3 level means you can get 5 level output. Okay. And this is the generator speed. You can see that the generator speed varies like this. And also the generator power also exactly varies that way. That means your controller, what you have designed, that is working for both the enhanced or fast dynamic system, and plus it also have maximum power point tracking. So that is how this power generation is exactly similar to your wind turbine speed. But there is one problem. That what is that problem? The problem is that when you have a 2 capacitor, you can see here in this figure, the C1 and C2, 2 capacitor, and one capacitor is charged to 550 volt. Another capacitor is charged to 250 volt. So if 2 capacitors are two wrongly charged, one is full, another one is half of that one, then when you have a switching action takes place, it will destabilize the system. So you need to balance this DC link capacitor voltage. Okay, this voltage need to be balanced. So we have used a balanced circuit. For example, C1 is charged high and C2 is lower charge. Immediately, based on a comparative statement, the S1 is turned on. Whatever the charges C1, it will give to L1. And L1 will absorb that one for some time. And L1 then feed to the C2. So this is the way that how we are balancing our DC link capacitors. After balancing, you can see that both the DC link, they are remain at 400. Then we have studied the voltage fault ride-through capability of the wind turbine. There are 2 types of ride-through capability. Voltage ride-through capability are 2 types. High voltage ride-through capability, low voltage ride-through capability. High voltage ride-through capability, that when it will, you have a 1 per unit, and when it will go beyond 1 per unit, then that is called the high voltage ride-through. And when it is going down from that 1 per unit, that is called low voltage ride-through. And that is what altogether about the fault ride-through capability. And what is that one? The turbines should be connected to contribute to the grid in case of disturbances. If any grid has disturbance, turbines should be connected. Why? Because sometimes, I don't know whether you people will are knowing or not. In the village, generally, the ladies carries the big pot of water. So when somebody from the backside will come and push it, so immediately there will be destabilization. Because of the destabilization, there may be unbalance. And due to this unbalanced system, there may be that bucket may fall down or that lady may fall down. So that is what the turbine, similarly, when you remove the disconnect turbine immediately, the whole network will become collapse. Sometimes it will collapse. So turbines should stay connected and contribute to grid during the disturbance also. And this we should supply both active reactive power for frequency and voltage recovery. You give the for example, power, again regain the speed. Again, you give some something, again you regain or you decrease this. So this is going on. This is so anyway. This is the grid code which is required. That till 15% of the voltage, it should be connected with the grid. And this is the Spanish and German grid code where we were working in one of our project. So the analytical study of pulse right through, this is we generated this voltage. You can see that from 400 volt, we developed this around 60 volt, okay? So this deep voltage, that one you can see here, the phase current here, phase voltage and current. Although they are very, you can see that always this voltage and current, they maintain unit perfect. And this is you can see that this is the voltage sag. The voltage sag is, you can see that for this period of the time, there is a voltage sag. As soon as there is a voltage sag, you can see that DC-link voltage oscillations come. And these are the DC-link voltages. And this is the modulation index. You can see that when the voltage comes down, the modulation index goes up because to balance the load power. And this is the neutral current during the voltage sag. And these are the capacitor voltage you can see, and this the right hand side is a simple voltage capacitor, each voltage across each capacitor. And this is our modulation index. When there is a voltage dip, you can see that modulation index became over modulation. That means it acts like this over modulation. Okay, this is over voltage. And then this is the grid voltage. You can see that when the grid voltage decreases, the modulation index is less than your modulation index is less low, then you will get two-level converter output. When it is high, you will get three-level. Then we will see the modeling of the grid-connected system with this is a very recent paper, came in IEEE Transaction and Industrial Applications. And you can look into this paper. This is very systematically designed. And these are the current source inverter where we used in that paper the voltage source also. So current source inverter, you may not have seen any 2-3 papers are there. And the current grid connected system with the current source inverter. So you know that VSI is used everywhere, voltage source inverter, but this is a current source inverter. First in current source inverter, you require any unidirectional switches. So here, so these unidirectional switches are, you can see that if you have IGBT, put a diode in series with the IGBT, you will get that this is a unidirectional switch. In VSI, you require bidirectional switch, and current is bidirectional. So you can know that there is a flexibility in the VSI, whereas in CSI, the current are unidirectional and the voltages are bidirectional or bipolar. You can see that this is that is what the CSI. This is we can make. We have a solar. And then we have a large inductor that behave like a constant current source. And then we have an inverter, and then we have filter and connect into the grid. So if you see that, then this is the controller. You have a PV array, and exactly this is the large inductor. And then we have a three-phase current source, and we have a filter circuit, and after filter connecting to the grid. So you can see here, this is the control block diagram where we do the MPPT algorithm, everything we do. Then this is the mathematical modeling. I am not going detail of this mathematical modeling. You can see the papers and find out this. Okay, if you have any doubt, you can ask me. But this mathematics, we are not going to deal here. So this is the system where you can model by using mathematical modeling of the system. So complete system, you can see that this is the plant, and this red color is the compensated system. So as it is a compensated system, so they are very stable, because you can see from this phase margin and gain. Then what are the constraints for current source inverter? Why you cannot use like a voltage source? No, you cannot use, because there are 6 switches and 2 switches, one switch from the top, one switch from the bottom must be on. So when you have connected the source, and if sometime, here, if one inverter switch and the top and bottom and then one switch on, then the converter will work. If there is no switch on the path of the current, so immediately they will destroy other switches. And another thing is that when the waveform are having undesirable characteristics, for example, in the upper one switch on, lower 2 switch on, then when 2 switches and upper 1 switches, that will create another uncharacteristic harmonic. Like harmonic is an integer, but we will get harmonic in the term of 2.5 th harmonic, like that. That is called the undesirable harmonic. And then we have 6 active switches, and there are 3 null switches. Null switches means when upper 3 switches are on, or lower 3 switches are on, or middle switches are on. So these 3 are given here, and this is the active voltage vector. And then we have a decoupling and gate signal. And this is what distilling current track. You can see this is our 15 ampere is given here. And this is our, you can see that it is always try to follow the references. So then we have similarly the current injection to the grid. You can see that both current and voltage are unit power factor, and the feed. That is why it's another name is utility friendly converter system. Utility friendly. That you are not generating any harmonic, rather you are giving this is what. And this is the modulation index. You can see that it is less than 1, and this is the distilling voltage. Okay. And this is the 3-phase current source inverter feed output current. You can see that they are 120-degree phase apart, and this is the phase utility grid voltage. Okay, this is the grid voltage and grid current, both are in the one power factor. And this is our FTP calculation. So the first Fourier transformation, and this is our this is you can understand that the magnitude of this one, and this is our output filter inductor and capacitor voltage. Okay, and this is our filter current in phase A. You can see that it is exactly showing these are the error signals. And this is to understand the robustness of this PLL. We deviate the PLL by 2 Hz. So you can see that within one cycle, they are able to track the actual voltage, whatever. So this is called the PLL. And this is our experimental setup, that this is the right-hand side is our rectifier circuits. And then we came here. So here you can see that this space is here. Again, we have a voltage current sensor port. There are loads, and also there are, you can see that there is an interfacing transformer which connected with the grid also. These are the few results and this one, and this is the anyway. So analysis and study is recommended. The model required various studies. We have done now load modeling, source modeling, as well as then we model the components of that one. Now we will study another concept altogether. So typical microgrid, we have a energy management, voltage control, frequency control, transient stability, protection. These are the electric vehicle, DR sizing, ancillary service, power quality. So load model, you can see that there are a structure of two generic load models. They are steady state and dynamic with different loads. And current source based load model are preferred because we always, in case of a power electronics. So what kind of load we consider? We consider always a current source load with infinite power for absorption and also giving back. So these are the differences. Then grid connected inverter with reference to active reactive power. This is the grid tie inverter and a transformer and choke and three-level phase and three-level three-phase inverter circuit. This is the controller for that one. And now we discuss what is the current method of simulation. First, we should understand that power flow analysis is very important. Then dynamic simulation. Okay, there are Gauss-Seidel method, Newton-Raphson, fast decoupled method. So many are there. I am not going to discuss. Dynamic simulation are required the transient stability, and then the economic dispatch and optimal power flow is the linear quadratic programming technique. You will use and then fault analysis. Load frequency control, operator training simulator, reliability modeling and simulation of the power market. The complete method of simulation of each component need to be connected there. That is why you need to here I think I have not given the transmission model data also is needed. So what is the information and communication? You have a local load and data link. So then network layer, then transport layer, some application layer. So if you see here the communication, there is a home area network. So you have a local area network and wide area network. So where you will do, that is also, if there is a paper by Professor Arindam Ghosh, he has given the standardization of the communication protocol for microgrid application. He has given, if this is the range, you use this technology. If this is the range, you use this technology. So this is, he is very nicely given there. And so I have time or can any?
Yes, sir, time, sir.
Okay. Kitna time hai? How much?
Sir, up to 1:15, sir.
1:15. Okay, 10 minutes. Okay, 10 minutes I will finish. And anyway, I will just finish the design part then. Because nowadays, why I am speaking the communication, information, data, everything, actually, because today we are not no more only electrical engineer, power engineer. We are all together, we need to learn to understand the complete view or holistic understanding of a research proposal and project. And unless in the research proposal we do not add these components into research, very difficult to get nowadays the research projects. Then there are also the system requirement and the system studies. First thing is that whatever network model you design, then microgrid design, then we plan. Then we will study coordinated study because all this system, you have a bus, circuit breaker, transformer, generation cable, all you need to coordinate everything. For example, I have a 4 sensors. Which sensor will first it operate? Whether the voltage sensor will operate, whether the current sensor, whether my data storage sensor will operate, what sensor will operate first. And then after that, we have a different category that DER set limit with their the distributed energies, because these are the limited energy source. It is not the infinite bus. Okay, so that is why the limit are needed. And then we have the characteristics of the protection device, and there are formal limits. Okay, then we have a load flow and again short circuit analysis where you get the data. So how to plan? First thing is modeling and simulation. Okay, so you required all this modeling, simulation are required, and simulating tools of CAD, softwares, other things are available. And that then we use the power system simulator for the microgrid design. One is the high initial cost software. You cannot design very complicated things that you need a very high cost software. So the purpose of this proposal is to develop a low cost or the free software by which this planning microgrid design can be done. And there are also, you can put a different kind of optimization and to the microgrid. Building component library for the microgrid, and especially the open source we use, and then validating the microgrid you have designed in a practical test way. So this is what the system, how we the design. We have you have specified, okay, the graphical user interface base description. Design a microgrid with generation capacity of this. There is a dash. You just put the generation capacity, put the peak load, and what are the renewable specifications you have. Then automatically it will generate a initially microgrid structure according to the required standard and capacity. So when you get a microgrid structure, for example, automated generation of initial discrete event model of the microgrid, you got this microgrid. But this microgrid is not optimized according to cost, according to the configuration, distance, wiring, components, everything needs to be optimized, that one. This has given a blank structure of the microgrid. So when you have a like this microgrid, so different components, and that you need to be optimized. Once it is optimized, then you can have a simulation and compilation, and then we have this structure, and this structure you need to be optimized, and then get the proper structural of the microgrid. So step one, that you initiate the specification, and then you develop the microgrid, automate, and then take the components from the microgrid library, and then decompile the optimization problem. Then you find what is the proper structure of the microgrid, then you can give then you can generate the test bed for the microgrid. And if you see here, we have developed the software, okay, based on the Open Modelica, okay. So this software and we developed this specially IIT Kharagpur professors they developed, and my job is to develop according to their design, I must develop the hardware setup here. So this is how the graphical utilization. Then we have a software tool for the DER, then we have a microgrid model, then open component library, and the simulation interface and interface with the high voltage. Then these are the components we have developed, that line, rectifier, battery, PV panel, and these are the samples of those components we have developed for this. And then there are also the scheduling other things. So this is the hardware design that you can see here. There are two pre-transmission system we developed in the laboratory and feeding different kind of the power. For example, the sun power or the wind turbine power, everywhere. So everything need to be modeled and integrated with this one. And then we will see the PV-enabled grid integrated microgrid for transmission system. So this is a simple microgrid structure and connected through a big transmission line. And hardly in India, we study the big transmission line when injected with a large amount of the renewable energy. What are the effect? So simulation study we did, but the practical thing very few people they have studied. So this is the proposed system. We have a solar, we have a wind, and connected to the load and the storage. So this is the distributed generation different control, and I am not going. And we use a proportional and resonant controller. You can see that this is the magnitude and phase of that controller. And this is the complete transfer function of the complete system. And here you can see this is our long transmission system. This can work as a long transmission system, medium transmission system, or short transmission system. These three are possible. You can see here, all these components are below. You can see in the below, they are inductors, which is acting like this inductor act like a transmission line. What is the transmission line? Whatever inductance per kilometer is mentioned here or given, that is given accordingly, that inductor. And this black color is the capacitors. They are the stray capacitance in a transmission line. These are the few specifications, and these are the few results by which you can see that both the current and the voltage are present. Here 80 kilometer, 240, and this. And this microgrid, and this is the transmission system. That the transmission system is, this is given here. You have a solar, wind, and grid connected to this one. And the smart meters. And we have modeled by using ABCD parameter. You can see that these are the. So this is what our transmission line. You can see this is the transmission line. And how you test it? You will test by using the Ferranti effect. That when you pass applied voltage, the Ferranti effect that your load end voltage will be higher as compared to sending end voltage. That is what we have studied here. And this is the simple simulation, and this is also one of the best project that Power Grid Corporation of India, they want, and this is the Power Grid work, and then we have I will show you maybe that video, and then I'll stop here. Just 1 minute. So this is our there are a lot of projects, but I have just so you can see here, this is the smart transmission system. Okay, thank you very much.
Thank you, sir.
If you have any questions or comments,
Any question, please? I think no question.
okay.
Good morning, sir.
Good morning.
Am I audible, sir?
Yes, yes, yes.
First of all, happy New Year, sir. So this is Manoj Kumar Kar, a research scholar from NIT Jamshedpur. Sir, first of all, it was a very nice and informative session. Sir, regarding presentation, I have one doubt, sir. Sir, while designing the controller, like voltage controller or current controller, so how we are going to tune the control parameters like AP and KI? As we know, in inverter part, we cannot implement optimization. It is very difficult process. So how we are going to tune these parameters?
First, actually, theoretical simulation when you do, first you try to increase or try to get the steady state values perfectly. You use KP, okay? The proportional gain, you go tune so that it will reach the steady state. For dynamic condition, you then tune to I controller. Generally, we design this one by using your border plot. You can design
Yes,
that.
root locus also we can.
You can use that also. You can get that parameter, but those parameters will not be properly work
Yes,
when you put in the actual system.
Yes, sir. Yes, sir.
Whatever your simulated parameter will not work in the actual system.
Yes, sir.
That is why when you have an actual system, you put P controller, because the I controller change, the dynamic of the system will be very little change. When you put just a P controller, you will see that the P controller will change this dynamic together, and whatever you found here, you must give more P controller there, higher P controller. The gain must be very high as compared to this one. And then you see that if the current limit goes above, you decrease that one. If the current limit comes down, you increase that one. Just a little bit tuning, you will get a
Then, sir,
perfectly.
we have to adopt heat and trail method, sir.
Yes. That practically, because you do not know stray inductance altogether.
Yeah, yes.
One inverter you design, you
Yes,
use a bus bar, the stray inductance is less than 9 nanohenry. If you use the same as a wire or a strip, you will see that it is in millihenry. So you cannot design perfectly. And each switching state, you will have a different kind of parameter variation.
Yes, sir.
So that is why there you need to do by heat and trial. There is no other way.
Okay. Thank you, sir. Thank you, sir.
Perhaps no question from other participants. Thank you so much, sir. On behalf of FDP committee, thank you so much to Professor Dr. Ranjan Kumar Behera, sir, for accepting our invitation and share the valuable talk and enlighten us about the theme area. And it's really a marvelous presentation. And now the time of sharing the e-felicitation to our honorable sir. Please, Saurabh. This is a token of love from all of us to our respected Ranjan Behera, sir.
Okay, thank you very much.
Thank you, sir.
Anybody want any hardware help, they can come here and do their hardware search. Okay, thank you.
Okay, sir. Thank you, sir. Now, thank you all the participants for joining. And next session, we are having at 2:30 p.m., sir. So all the participants requested to join at 2:30 p.m. Thank you. Link will be shared. Same link. Thank you all. Thank you.